Swayam Prabha. Digital India. Educated India.
So let's start. We are doing dependency parsing algorithms, and one algorithm we have seen is called transition based algorithm, where you have the stack and the input buffer. Now that algorithm is greedy and has the difficulty that it always produces projective tree. And if the sentence is inherently not amenable to projective tree, the algorithm will produce wrong parse. Okay, so those difficulties are removed by graph-based dependency parsing algorithm, and the algorithm is based on maximum spanning tree construction. So let's see what is the algorithm's main idea. This is called edge factored scoring. So an argmax based computation is set up. Given a sentence and its spanning tree, we'll come to the tree part later. The score is computed by the scoring function, and score s comma t. T goes over all possible dependency trees of the sentence. Okay, and whichever tree has the maximum score, that is the tree which is returned because of this argmax. Now score of s comma t is computed by summing the scores over all possible edges. So the edges actually belong to the tree, and the score of edge is obtained by a weighted sum of the feature function of the features. Now this kind of scoring you are familiar with. For chunking, for example, you had to raise this kind of quantity to the power of e. Okay, and then find out the maximally scoring chunk. So here also we will find out that tree which has the highest score, and the score is computed by summing over scores on the edges, and these scores themselves are sigma wifi, or dot product of two vectors w and f. Now features are pre-designed. W's are found out by training a machine learning model. So we'll come back to the training data creation very soon. So these three equations are the guiding principles for edge factored scoring of the dependency tree. So the basic idea is very simple, right? That if I have a sentence and I have all possible dependency trees, then I have a scoring function by which I can choose the best possible tree. And this algorithm doesn't suffer from the projectivity constraint. Okay, it will produce the tree independent of whether projectivity is maintained or not. It can produce non-projective trees also. A non-projective tree, you would recall, is a tree where crossing of arc can happen. And crossing of arc is because of all the edges are on one side of the sentence. Okay. So let's go into a little more detail of this framework where we have to score trees. Now, spanning tree is a well-known concept in data structure and extremely useful. So if I have this graph, undirected graph, A, B, C, D, where the edge weights are also given. AB is 1, BC is 2, CD is 3, DA is 4, DB, the diagonal weight is 5, AC, the other diagonal weight is 6. Can somebody verify you are seeing the spanning tree on his rectangle?
Yes, sir.
Yes, sir.
Okay. So you can have many spanning trees out of this undirected graph. The simplest possible is a linear chain A, B, B, C, C, D. Okay, and the weight of that tree is 1 plus 2 plus 3, 6. Now the definition of spanning tree is a tree which spans the whole graph, that is, includes all the vertices of the graph, okay, in its vertex set. The tree is a special case of a graph, and the graph gives rise to the spanning tree. The word spanning means it spans all the vertices. Now, two trees which are of special interest are minimum spanning tree and maximum spanning tree. So it turns out that this linear chain has the least weight when you sum all the edge weights. So that comes out to be 6. Another spanning tree can be A rooted at A with children being B, C, D. And the edge weights are 1, 6, and 4, which is 11. But that is not the maximum spanning tree. It is not the tree which has the maximum weight, maximum total weight. This tree, which is A goes to D, A goes to C, and C goes to B, is a tree with summation of edge weight as 12, and that is the maximum spanning tree. So minimum spanning tree can be found out by what is called the Kruskal algorithm, which is a very well known and very instructive algorithm in data structure and algorithm course. So if and same idea can be used to find out the maximum spanning tree. How does it relate to our discussion? So finding the dependency tree amounts to finding the highest scoring dependency tree, and which is same as finding the maximum spanning tree for the sentence given a complete graph, okay, complete graph over the words in the sentence. So you can roughly get the intuition. Okay, so this is the maximum spanning tree based algorithm, a very famous algorithm in dependency tree finding. Now we proceed and we ask what should we score? All the probabilistic methods for NLP, the probability is used for scoring. But what do we score? We need an object on which the scoring function should be applied. So we recall that in part-of-speech tagging, we score the paths on the trellis. The trellis is generated by a trivial algorithm. Simply erect the column of states on each word. People jump high. So on people, you produce noun, verb, adjective, adverb, all those tags. Similarly on jump, similarly on high. So that is called the trellis. And we find out the best possible path from the sentence beginner to sentence finisher. So the object we score in case of part-of-speech tagging is a sentence beginning to sentence end. In probabilistic constituent parsing, what do we score? We apply the probabilistic scoring function. That probabilistic scoring function is nothing but product of probabilities of rules which are applied to generate that tree. But to be able to score that tree, we have to have the tree first of all. OK, and that tree is found by the CYK algorithm, concentrating on rows and columns in the word by word matrix for the sentence. So in probabilistic parse tagging, we score the paths. In probabilistic constituent parsing, we score the parse trees. Now here what happens is that we are concerned with efficiency, not only because there could be exponential number of entities to be scored, but also because we do not want to stupidly keep doing the same computation again and again. So when we do part-of-speech tagging, This is the trellis. People jump high. So these these are the words. People jump and high. And the trellis is this set of part of speech which are assigned to each position. So the column of part of speech is shown here. Okay, and then we have these transition probabilities state to state and the emission probabilities state to the word. So you see if I take, for example, um, any partial path and compare this with a previously created partial path, there is so much which is common between these two partial paths. If I take hat n and v, and hat v and v, then hat n and n, hat v and n. So in these paths, these edge computation, okay, hat to n and hat to v, is done repeatedly. And if this has been done once before, why should I compute it again? I can simply use that value in the expression for partial path. So that is the idea of dynamic programming, and Viterbi algorithm does a very good job of this. So brown foxes jumped over the fence. You will recall in part of speech tagging lecture. We go from the sentence beginner, develop the children, grandchildren, grandchildren, and we only advance those paths which have the highest probability amongst all those paths ending in the same state. So this is the Viterbi algorithm, and it works because of the Markov assumption. So here we see an interesting thing. There is joint generation and scoring, right? The exponential tree is implicitly there. While traversing, we generate the partial paths and we also score them. And at the end, we find out the best possible part of speech diagram sequence. A similar idea is used in probabilistic constituency parsing also. The gunmen sprayed the building with bullets. The positions are placed on the rows and the columns. The column positions are advanced by 1. So that you can ask between 0 and 1, what do I have? I have a determiner here. Between 0 and 2, what do I have? I have a noun phrase. The gunman is indeed a noun phrase. And while we do so, scoring the partial trees, just like we keep scoring the partial paths in pause tagging, we keep scoring the partial trees in probabilistic constituency parsing. And this is also a dynamic programming based algorithm. It is called inside outside algorithm. I have mentioned this algorithm many times, but have not really done it in the class, though the slides include how the computation is done. The computation is done by finding out the beta or the inside probabilities and multiplying them and taking their sum over through marginalization. So all this happens together, generating partial parse tree and generating the score. So the same idea is carried over to dependency parsing also, and to many such situations in natural language processing. There is a slight difference which comes, major difference I would say, which comes when we resort to a different computing paradigm, namely a neural network based paradigm. Okay, so there the scoring mechanism is opaque to us. The neurons interact with each other, information flows over the edges, and thereby the computation is done, score also emerges. So let us remember this point of partial answer generation and scoring it. Okay, and many times greedy approach, dynamic programming approach, they are the foundations on which these algorithms are built. Now the algorithm, which I will not be able to discuss in complete detail, but it's a famous algorithm for graph-based dependency parsing generation. Again, this is from Jurafsky and Martin. It is called Chu Liu Edmonds graph-based Edmond's algorithm for graph-based dependency parsing. So very roughly, if I take this sentence, book that flight, these numbers indicate something which, if I find time, I will go into. But this algorithm is an elegant and easy to understand algorithm. So from the root, we eventually want an edge onto the main verb, which is book. And from book, there's an edge to flight, which is the object edge. And flight is modified by that, which is a determiner for flight, book that flight. OK, so this algorithm produces progressively a tree, but not really a pure tree. There are cycles, and then there is another phase of the algorithm which removes this cycle. So please take a look at the chapter which I have circulated on, which has been circulated on Teams and Moodle both, and the algorithm you can follow. Now, the time complexity of the MST algorithm is like the minimum spanning tree algorithm, which is order of number of edges into log of number of vertices. E is the edge set, V is the vertex set. So, so then we are talking about order E log V, and think about whether this is linear or quadratic in the sentence length. OK, sentence length is the number of words in the sentence length. So please put this as an exercise. In the MST algorithm for dependency tree finding, express complexity in terms of sentence length. In part-of-speech tagging, the complexity of the algorithm is the complexity of the Viterbi. OK, and that is orders tag set square into the sentence length. OK, so here also you can think about what would be the complexity of the algorithm in terms of the sentence length. Is it quadratic, linear, cubic, and so on. Now, when we do the scoring for dependency tree, we do the scoring based on features, and the features which are used are word forms, lemmas, part of speech of the head word and its dependents. OK, so book that flight. Here, when we give the weightage to the edge between book and flight, book is the main verb, flight is the object. When we give weightage to that edge, we have to use the training corpus, namely the already created dependency trees. And the W into F, OK, the dot product of weight vector and the feature vector. So feature vector consists of word forms, lemmas, and part of speech of the head word and the dependent. So I need the features of both book and flight. Corresponding features derived from context before, after, and between the words. Word embeddings are also used. So you probably are relating very well to this because of your chunking assignment, which you have done as the second assignment, I believe. The dependency relation itself is also coming as a feature. The direction of the relation to the right or to the left, and the distance from the head to the dependent. OK, so feature engineering is completely in our hand, and we decide based on our insight into the problem what the feature should be. But one thing I can tell you from my experience of working with different NLP problems, the word and the part of speech tag of the word is almost a universal feature for any NLP application. Whenever you see machine translation, sentiment analysis, question answering, inferencing, everywhere we do see that the words themselves, now the words become word embeddings, and the part of speech of the words are the features which are never dropped, almost never dropped. They're always used. Okay. Now it is useful for you to think about why these features are included. For example, the direction of the relation to the right or to the left. Why is that important? Okay. So we know normally the object relationship will be a right arrow because the object comes after the verb, subject comes before the verb for English. But for other languages, this is not the case, and this feature will have to be judiciously used. Now, all these features and their weights are these days exploited in neural graph-based dependency parsing. The paper in 2017, there are papers in 2017, Zeman et al. And Dozat et al., which give the state-of-the-art algorithms in multilingual parsing based on RNNs, based on recurrent neural networks. So now this gives us the lead for starting discussion on recurrent neural network. You have got feedforward neural done, and feedforward neural network gives rise to convolutional neural network. Okay, the closest modern day powerful machinery is CNN, convolutional neural network, which is used more in computer vision, image processing, pattern recognition. But NLP uses more of recurrent neural networks because sentences are sequential structures. So we would like to begin discussion on recurrent neural network, and you'll see that the main idea is not different from feedforward neural network. So feedforward neural network, CNN, RNN, you can say that deep neural networks are essentially three computing frameworks: pure feedforward network, convolutional neural network, and recurrent neural network. The three big umbrellas, and they're combined also. After CNN stages, you typically have the final stage as a feedforward neural network, fully connected feedforward neural network, which is also called a dense network. Dense network because all the neurons are connected to all other neurons in the previous layer. So let's begin recurrent neural network, and let me straight away go to BPTT, backpropagation through time. Okay, that is the essential idea behind RNN. And so suppose I have a recurrent neural network here. Okay, and it is the same neural network which is shown in 3 time steps. Okay, so W1, W2, W3, W4. These are weightages at different time steps. Okay, so from the first state, the first circle, I go to the next circle, then to the next circle at different time steps. And this network is actually equivalent to a network feedforward network that is unfolding over time. Okay, so at time t equal to 0, we have these 3 neurons. Okay, then these 3 neurons give rise to the same 3 neurons. Okay, I'm sorry, these 3 are not states. Actually, these 3 are neurons. The same 3 neurons are repeated in the next time step. In the next time step, again, these 3 neurons are repeated. Similarly, at time equal to 3. So for NLP, what does this picture denote? So if this network is looking at every word in the sentence, then if there are 3 words, then at time 3, this kind of unfolding will stop. Okay, and we look at this unfolding and the state of the neural network influencing the state of the neural network in the next time step. All this we look at in the next week. But you can see this unfolded recurrent neural network is amenable to whatever discussion we did before. This unfolded recurrent neural network is nothing but a feed-forward network. Okay, and the connections are not really full in the sense that not everything in one layer is connected to all neurons in the next layer. This is not the case. You have to replicate the connection in the original recurrent network. So we see connection from first. I should have named them the first neuron to second neuron. Okay, and then second neuron connects to third neuron through W4. So so this neuron, you can see the middle neuron connects by W1 to first neuron and by W4 to the third neuron. So the computation as it happens is as if there are multiple layers of neurons which are connected in a feed-forward manner, obeying the constraint that the weights should be same wherever they are same. Okay, I'm giving a very rough idea. Next week we will elaborate this totally. So when I have this feed-forward network, I can apply the backpropagation algorithm. So this backpropagation algorithm is called BPTT, backpropagation through time. Backpropagation through time. Let me see. I have it here. No, it's called backpropagation through time. And the same derivations which are used for backpropagation, namely hidden layer neurons, weight change, output layer neurons, weight change, all these formula apply here also. Okay, which is why I was saying that eta into delta J into OI is a universal weight change rule. So let me go back to some usage of recurrent neural network in NLP. So suppose I'm doing part of speech tagging, purchased Videocon machine. Purchased is VBD, past tense verb. Videocon is a proper noun, so NNP. Machine is noun. Okay, so this is the machine. This is the recurrent neural network which will keep looking at every word. Okay, and give the output. Give the output based on the current input and the previous state. Okay, so when the machine is seeing Videocon, it has the state information, which is a function of the previous input and previous state and also previous output. Okay, if VBD was output, then previous input was purchased, and these two determine the previous state. So that state is multiplied by W and is participating in the computation inside the second state. And there the output is NNP, proper noun, on the input Videocon. And it also gives rise to a state which is the input to the next state where the output has to be NN. Okay, so you can see conceptually that this is a very elegant framework which evolves over time. And this evolution over time can be simulated by a feed-forward network. Now, this is an example of a sequence-to-sequence transformer. Okay, the purchased Videocon machine is transformed into another sequence VVD, NNP, NN. And this is very characteristic of NLP, where machine translation as a whole is actually this framework. So purchased Videocon machine could also have been leading to a situation Videocon machine kharida, Videocon machine kharida. So that would be a Hindi sentence generated from the English sentence, and the output would be not part of speech tag but Hindi words. So we would like to take RNN and do some amount of machine translation discussion. From 21st, your NSEM begins. In fact, first day itself you have your NSEM. So we have just about 2 weeks, yeah, exactly 2 weeks of lecture, and I would like to do machine translation. A lot of things remain. I would like to take them up next semester when I teach deep learning for NLP. The other situation is for sentiment analysis. Okay, where I have the sentence I like the camera and end of sentence. Now, by processing this sentence totally, I come to a level positive sentiment. I like the camera is expressing positive sentiment about the camera. So the output is positive sentiment. So this is a classification problem. Positive sentiment, negative sentiment, and neutral. I like the camera. I dislike the weight. That would be a negative sentiment. The camera cost me 5,000 rupees. That's a neutral sentiment sentence. So this is how the recurrent neural network processes this. It doesn't output at every state, unlike part of speech tagging or machine translation. It outputs at the end, and that is the output level of the sentence. So there are two kinds of situation, output at the end and output at every step. And there are NLP applications which demand both the situations. This is also reminiscent of something called encoder. Okay, so if this is an English sentence, I like the camera. Then the normal situation is you encode the sentence. The encode comes at the encoded representation comes at the end of the input, and that encoded representation goes to what is called the decoder, which again step by step produces the sentence. I like the camera. मुझे यह camera पसंद है. So that will be produced by the decoder. Okay, so we'd like to look at this combination of two RNNs or two LSTMs or two bi-LSTMs to produce machine translation. So a bit of machine translation theory and how this transformation takes place we'll do. I'd like to stop the coverage of content at this point of time, and I'd like to discuss the last quiz. So let me open the question paper. The sentence "the book makes available stories not easily accessible" has how many dependency trees? The answer is 2. Okay, the book makes available stories not easily accessible depends on where you put the pause. The intended meaning is the book makes available stories not easily accessible. So stories which are not easily accessible are made available through this book. Okay, so this is one meaning of the sentence. But there is another strange meaning. It doesn't make sense, but it is a valid tree. The book makes available stories not easily accessible. Okay, so here available is an adjective for stories. Right, so that is a very strange meaning. Stories which are available, they are made not easily accessible by the book. So that is the other meaning, and they will give rise to two different trees. Okay, so first senses makes available. Makes is the main verb. Then there is book, and there is the. Okay, so makes book the subject is taken care of, and then makes available. Okay, so makes available. And what does it make available? Okay, so here makes the book available. stories. Sorry, this would be stories. Stories. And what kind of stories? Not easily accessible. Here, accessible. And then easily. I should have placed stories properly. And then not. Okay, so not easily accessible stories forms one unit. Noun phrase with adjectives. Not easily, easily accessible stories. Okay, and these are directed graphs. So from makes to stories, stories to accessible, accessible to easily, easily to not. And makes available, available comes as child of makes, and book and the. So this is the reading that is intended for the sentence. The other meaning is makes available stories not easily accessible. Makes available stories not easily accessible. Okay, so how will that tree look? Let us see. Yes, great. Okay. Now available is an adjective for stories. And here you see the dependency is between stories and available. Okay, so makes available stories not easily accessible. Okay, so I can put a arc here. This is also a directed graph. So it has some strange meaning. Okay, you could also, of course, I think you should do this. Yeah. Okay. So this will be another tree. The book makes stories not easily accessible. What kind of stories? Available stories. Okay, so these are the two parse trees, and you have to show that you have to take the correct answer. Next question depends on this, but let me take question number 3, which was again deceptive. Okay. All the model answers, of course, will be to you very soon. Question number 3, let me bring it up on the screen. Can you all see question number 3? A feedforward neural network is one in which the connections strictly go from layer to a layer closer to output layer. That is, if the input layer is given the number 0, the next layer is 1, next layer is 2, and so on. Connections grow from layer I to layer j, where j is strictly greater than I. The minimum number of hidden layer neurons needed to solve the 2-input XOR problem with an FFNN is 1, 2, 3, 4. The answer is 1. Okay, how is it 1? This is the output neuron. This is the hidden layer neuron. And these are connections from X1 and X2. And X1, X2. And there are two connections going like this. And one connection coming like this. Okay, and this computes XOR. How does it compute XOR? So this weight will be 1. This weight also will be 1. Okay, now these weights also are 1 and 1. Okay, now if everything is 0, if both the inputs are 0, output should be 0. That can be achieved anyway. When the input is 1 and the one of the inputs is 1, then this neuron should fire. Okay, so I can achieve that. I can achieve that by, for the moment, ignore the hidden layer neuron. So if I have threshold as 0.9, 0.9, then any of the inputs being 1 will cause it to fire, provided the influence of this neuron is not there. So let me not output anything from here. Okay, when one of them is 1. When one of them is 1, nothing should be coming from here. So I can make the threshold here 1.5. 1.5 is the threshold here. So when one of them is 1, nothing happens here. The output is still 0, so it doesn't influence. So 0 for 0, 1, the output will be 1. Output will be 1. The problem is what will happen when both the inputs are 1, x1 and x2 both are 1. When both of them are 1, this will fire. Okay, this will fire. But I do not want, and I want that to influence the computation here. When both are 1, the output should be 0. Okay, so now if I have a negative value here. Okay, if I have a negative value here, let's say -2. Okay, then the output will automatically become 0. So the role of this hidden layer neuron is to suppress suppress the effect of the input by subtracting something. So this network will compute XOR just with one hidden layer neuron. Okay,
sir.
Yes.
So in the question, it is mentioned that the layer, each layer will be connected to the next layer. Only one.
No. It didn't say next layer. Did it say next layer? The connections strictly go from layer to layer closer to the output layer. That is, if the input layer is given number 0, next layer 1, and so on, connections go from layer I to layer J, where J is greater than I. I'm not saying J equal to I plus 1.
Yes, sir. Okay. Yeah.
Yeah. So this question was deceptive. Weighted majority is linearly separable, and odd parity is not linearly separable. If odd parity, that means the number of ones in the input is odd. If odd parity was linearly separable, then XOR would be linearly separable. XOR is a special case of odd parity, where the number of ones is odd. Okay, so odd.
Yeah. So in this, there is a special case too when the number of inputs are equal to 1. So then it becomes linearly separable. So it can be. Sir, there's a special case when the number of inputs is equal to 1. So in that case, it becomes linearly separable. So
No. The definition of odd parity function is that in the input, the number of ones should be odd.
Yes, sir. So in the case when there is only one input, we can easily separate it.
So for 1, the output should be 1. For 0, output should be 0. Yeah.
So yes, I've written both A and B. I've given the explanation too.
Okay. So a very special case is where the input length is 1. Is that so?
Yes, sir.
Okay. However, in general, odd parity function is not linearly separable, but weighted majority function is linearly separable. The number of ones should be greater than number of zeros. So you just have to design the threshold properly. So suppose the number of input length is n. Okay, if the input length is n, then n by 2 minus delta should be the threshold. Then weighted majority function will be computable, and this is linearly separable. The only question that is remaining is question number 2, where you are supposed. Yeah.
Just to clarify, so in the last question, even if you write both A and B, that would be correct, right? Because it's multiple answer question.
Okay.
I've written the explanation for both two, and I've written both A and B is possible.
That's because you took the input length as 1 and also input length as more than 1.
Yes, sir.
Did you know that if the input length is more than 1, it would be not linearly separable?
Yes, sir. I've written that in the paper.
Yeah. What is your proof?
Sir, for what?
For more than one length input, why is it not linearly separable for odd parity?
So means if there is a hyperplane, means basically in the if we means I just visualized it in the n dimension space. So it's basically positive and negative classes are getting alternated. So hence we can't find a linear separable. If we find means means it was just by visualization I did mainly.
I see. Yeah. Of course, I mean another argument would be that if two input odd parity is linearly separable, then XOR is also linearly separable. Yeah. Okay. So we'll discuss the second question also, that has a little bit of complexity.
Bara has also asked, why can't we count 4 parse trees as follows? Available as adverb to the main verb, makes, and not easily accessible, qualifying the main verb makes. That is the first one. Second is available as adverb to the main verb makes, and not easily accessible, modifying the object stories. Third is available as adjective to stories and not easily accessible, qualifying the main verb makes. And the fourth and the last one is available as adjective to the main verb makes and not easily accessible, modifying the object stories.
Available can never be adjective can never qualify a verb. Adjective has to qualify a noun. Okay, but I see some interesting possibilities that you are talking about. So we'll look at your answer. Have you given all these possibilities in the answer?
Yes, sir. I've drawn all the 4 parse trees. And the fourth, I actually miswrote it. I meant available as adverb to the main verb makes.
So the first parse, where we are saying makes available, story is not easily accessible. That makes available, that first parse actually available is attached to makes. Available is not really an adverb to makes. Okay, it has a different status. This is what is called a light verb. Okay, so make available, make a presentation. Okay, do a presentation. Here, these verbs are called light verbs. So we'll discuss that. And available is still an adjective. Okay, still an adjective. It is not an adverb to make. But I'll look at your answer and see the possibilities.
Thank you.
Okay, thank you.
Thank you.